Looks like we're live. Hello everyone and welcome to yet another recreational programming session. How about that? Let's make a little bit of an announcement on our Discord server and officially start the stream, I suppose. Let me see. So I'm gonna do a red circle live on Twitch, right? And what are we doing today on Twitch? Today we're actually coding in assembly on Linux. That's what we're doing today, believe it or not. Right. And this is needed for one of the interesting feature for Porth, the programming language that we're developing in here. Right. Because it's a very like a low levelish feature that requires interacting with an operating system in a very specific way. Yeah, we continue to work on Control-C, but I don't think I'm gonna publish that previous Control-C stream because it wasn't really that interesting, right? So I didn't expect going into such a deep rabbit hole, right? So I did a little bit of research off screen, and I think this is basically gonna be my essentially report on how we're going to be handling the signals in Porth from now on. Right. Hello everyone. Welcome. So yeah, we want to implement an ability to handle Posix signals in Porth. Right. So let's actually Google up Posix Signals. Right. It's a very important feature that I think we should be able to support. So signal IPC. So basically it's a standardized message sent to a running program to trigger specific behaviors such as quitting or error handling. They're a limited form of inter-process communication typically used in Unix-like and other Posix compliant operating systems. So I'm going to actually give the link to this definition in the chat and also in the description, right? So the language that we'll be developing, by the way, is concatenative language. If you never heard about concatenative languages, check out concatenative.org. It's like basically a wiki that collects information about concatenative languages, and it's like a whole new world. Trust me, it's very, very interesting. So signals. So we've got some subs. Thank you so much, hey GVT, for resubscribing for 2 months of tier 1 subscription. Thank you. And welcome to our epic Porth club. So let me actually go and maybe update my Porth stuff. Maybe I'm gonna actually clean up. Yeah, so there's some stuff from experimentation. We're gonna clean everything up. And also I have some stuff in here. Maybe I'm gonna do git reset -hard. Very hard reset. And let me fetch the latest stuff. Right, so I'm gonna fetch the latest changes that I made to the compiler. Right. So I did a little bit of stuff off screen. And by the way, for the module Feng Shui lovers, I finally split my huge Porth file into several files, right? So there's a SFC folder, and as you can see, I have the main entry point, I have the Lexa, the compiler, the generator, the type checker, and so on and so forth. As you can see, everything split into these like components, you know, the standard compiler components, because something like Lexa, compiler, type checker, and code generation is like a more or less standardized components of the compiler. So I just basically split those into separate files. But there is still a porth.porth file here at the root, and the only thing it does, it just like includes all of the components of the compiler. And at the top, we're also going to have some sort of like flags that control like a global behavior of the compiler. So yeah, let's actually quickly bootstrap the compiler and try to recompile it with itself. So bootstrap phasm. Right, so here is phasm. I'm going to do that. Then I'm gonna make the bootstrap compiler executable because phasm cannot do that. Right, and I'm gonna recompile the compiler with itself. And as you recompile the compiler, as you can see, it just includes all of these components and compiles into a single executable. After which you can just keep recompile the compiler with itself. Right, so I just keep recompiling the compiler with itself. And yeah. All right. So we have that. So essentially how usually the Posix signal handling is happening, right? So imagine that you have some sort of a program. I'm going to be using the C for explanation, right? You have some sort of a program. And for instance, you have some sort of a signal handler, right? So let's call it handler, right? So literally call it a handler. And then basically what's going on, let's say caught a signal, right? Caught a signal. And then you have some code that performs some sort of a work, right? So while true, and you do some steps in here, right? So process, maybe it's actually not use comments, process one, then process some more data, process more, and so on and so forth. You have some sort of a code, right? So somewhere here, somewhere at the beginning of the program, you sort of have to, this is like a high level, logic on how you handle the signals. Like it's a very high level. You will basically have to tell the operating system what is the handler that you're going to be using for the signals, right? So you have to somehow register that handle, right? So you do register. I forgot that register is a keyword in C. Register handler. Let's call it register handler. Right, so you tell the operating system, okay, so here's my handler for the signal, and you move on doing your stuff, right? So, and you just like processing things. And what's interesting is that when a signal is sent to your program, the operating system will stop your program, like wherever it was, right? So let's assume that it was about to go into the process2 function. It will not go there, it will instantly stop, and the operating system will force your program to jump to this function and start handling the signal. That's how it usually works, right? You receive the signal, full stop, operating system tells you to do full stop, go handle that signal. That's how it works, literally, right? And you handle that signal, and as you return from this function, you actually return back to the place where you were interrupted. So at any point of execution, you can be interrupted. So yeah, this is something that people don't really usually think about when they program for Unix or Linux, is that you can be interrupted at any point for whatever reason, right? And you'll have to be forced to go handle these signals. So usually you have default handlers that do default things. So you don't have to think about that. But if you were to override those default handlers, this is how it would usually work, right? So this is like basically how all of that works. All right, we've got some subs. Root Black 45, thank you so much for 3 months of tier 1 subscription. Thank you, thank you, thank you. And SalaryBot, thank you so much for 4 months of tier 1 subscription. Really, really appreciate all the support. So, yep. And what kind of signals can you receive? Right, usually the most common signal that people handle in Posix operating systems is called the SIGINT. It's an interrupt signal, and it is very common because it's the signal that the user can initiate. Essentially, when a program is running and a user wants to stop the program, they usually press Ctrl+C. And pressing Ctrl+C sends SIGINT, the interrupt signal, to the program. And the default handler of that signal is just quit the program. But you can override that. In fact, as far as now, Vim, for instance, override that signal. So if you try to press Ctrl+C, you can't quit Vim by pressing Ctrl+C, because Vim overrode the standard handler for SIGINT, and every time you press Ctrl+C, it jumps to that handler and just prints this message in here instead of quitting. So it just handles that signal. So another signal that you can receive is segmentation fault, right? I think segmentation, like memory violation, is a signal that you can actually handle, right? Essentially, segmentation fault happens when you're trying to touch a memory in the places where you're not supposed to touch. For instance, that memory is protected for writing and you try to write in there. In that case, the operating system will just, snap your hands and send you a signal. The default handler for that signal is going to be just die. but you can catch that signal, and in fact with that signal comes a lot of interesting information. For example, with that signal comes the information what memory you tried to touch, which you can use for example, for debugging. Right, so you can write your own handler for, the chat actually sets sig serv, and I don't know where exactly it stores that information, maybe somewhere in a trampoline or something, but I heard it has a lot of information about like what exactly happened, and you can kind of like extract that information and do something with it. So this is another signal. Right, for instance, and it actually does fit the definition of a signal. You tried to touch a memory that you're not supposed to touch, and you instantly got interrupted. You instantly got interrupted and told, please explain yourself. What the fuck were you doing? Right, and the default explanation is just die. But the program can take an opportunity to actually explain or maybe do something when they touch the memory in an appropriate place, right? So... and there is different signals, right? So if we're writing a programming language, we want to be able to handle such signals. So there is another interesting use case for signals. For example, I already mentioned that Nginx, it also accepts signal. I don't remember which one. I think it's sig HUP. I don't remember what it means. I think it's like hang up or yeah. So it can receive this signal, and when Nginx receives this signal, it reloads its configuration, right? So essentially you can use this kind of mechanism to like tell the running process like how to reload your configuration or update something, which is quite convenient, right? So yeah, and we want to be able to handle this kind of stuff. So this is like a high-level description of this stuff. Nginx uses sig user1 to hot reload a running binary. Oh, that's actually pretty cool. So you can not only hot reload the configuration, and you can also hot reload the running binary. So it's a very, very dynamic thing. And as you can see, there is a lot of uses for the signals. And if the language does not support like handling these kind of signals, at least for Linux, I don't know what exists on Windows or whatever other operating system, but on Posix operating system we want to support, you're kind of like missing out a lot of things. I think language has to support this kind of stuff. Hello everyone. Okay, just a second. Okay, let's take a look at how you usually write the handler for the signal, right? So there is a lot of ways to do that, and as far as I know, the most portable one is sig action, right? So you would use this function, which is provided by Posix, right? It's part of the Posix standard, and what it does, it accepts the number of the signal that you want to handle, right? And then it accepts the description of the action to perform on that signal, and also you can get what was the old action. So because every time you set this action, you override the current action, but you may not want to lose what was previously, so you may want to save it to restore it later. So that way you can actually get what was before. And that's it. That's basically it. So the action is basically a structure, and within the structure you can provide a pointer to a function which is the handler. Right. And there's a lot of different masks and flags and stuff like that. We don't have to worry about them too much. So let's go ahead and just like implement this entire thing. So we'll have to allocate the structure for the sig action, right? So let's go ahead and do that. So it's going to be SA. By the way, MM2PL, I kind of want to make you a mod. Is it okay for you? Right, you're a mod now. All right, so let's go ahead and do that. So as far as I know, the handler accepts an integer. And the handler accepts an integer, and the integer is basically the signal that was issued. Right, so basically this is needed if you want to use the same handler for several different signals, and within the handler you want to distinguish what's the signal you're handling, right, essentially. So because of that, our handler has to accept integer, and we may say code signal D, and here is the signal. Right, so this is going to be a signal, let's call it something like maybe sig right, because as far as I know, signal is also a function in the standard library. Right, and here we're gonna just return out of this entire thing. Right, and the step of registering a handler is essentially going to be setting the SA handler. Is it called SA handler? I think it is called SA handler. Yeah, it is called SA handler. Registering it like that, right? So before that, it also makes sense to actually zero initialize the entire thing, right? So let's zero initialize everything, or we may actually do something like that. That way we don't have to use memset. And after that, we just have to give all of that information to sigaction, right? So the signal that we want to handle is sigint, and the action is our action. And we don't really care about the previous action. We don't want to restore it, so we're going to put null in here. So as far as I know, you can put null in here if you don't care, right? So, and this entire thing returns a negative number in case something went wrong. So if something went wrong, let's actually do something like this. Error could not set up sig action, right? Sig action, and we can put some sort of explanation in here. So it's going to be str error, error no. There we go. And then we're going to have like exit. Cool, there we go. So, and we may go on to maybe, I don't know, sleep for several seconds, or maybe, I don't even know what we can do. We can basically wait for some input from the user. Right, and to wait for some input from the user, we are going to allocate a buffer, right, 256, and just issue a read syscall. So this is going to be read. We're going to be reading from the standard input, which is 0, I think, buffer, size of the buffer. Right, so, and that basically stops the program and waits, and that gives us an opportunity to send an interrupt signal and call this function. Right, so, and let's do the print, saying something like OK, and that should be it, I think. Let's try to recompile the entire thing. So, I think I'm gonna create a separate folder called sig action, right, so for the explanation purposes. Right, so we're gonna have something like that, and let me maybe also create build.sh, which is going to build everything in here. So it's gonna be in... Okay, so I don't know why it took so much time, but yeah, it's just like Emacs being Emacs. Also I want to set xe, and also I want to make this entire thing executable. All right, so let's do a build. Shall we? Let's do a build. Okay, so here sig action, as far as I know, will need to include signal, right? So this is going to be signal. What's going to be the rest of the stuff? str error, that requires the string and the error no, if I remember correctly, right? Is that what it requires? Exit requires standard library, stdlib. And read probably requires uni-std, right, uni-std, there we go, so we have something like this in here. Cool, now let me maybe go to that place, so import sig action, and let's actually run this program. It's not going to do anything, but if I press Ctrl+C, it will say caught a signal to, and then OK. So the only place where we print caught a signal to is in here, right? So, and we never really explicitly called that function anywhere. We just like put it in a structure and send that structure to this function, and that is set it up. That actually properly set it up. So, does anyone have any questions so far? Does anyone have any questions so far about what we're doing? Okay. So, this is how you do that in C. This is how we do that in C, but we want to do the same thing in Porth, and this is where it gets complicated. Right, so in Porth, we can't link with libc for a variety of reasons. It doesn't mean that we're never gonna link with C, it's just like we cannot do that right now. And C library actually has a special place in sort of like a stack, in the development stack on Linux, right? So, oh shit, I just realized that my tablet has died, so I can't use my tablet to actually explain things. So I'll have to do some weird stuff. Maybe I'm gonna use Inkscape, but it's too bright. No, I can't use Inkscape. So I'll have to do the ASCII art. So okay, so imagine that we have a Linux kernel, right? So this is the Linux kernel, and right. So it creates this sort of layer, right? On top of Linux kernel, we have libc, right? Libc, which interacts with the Linux kernel using the syscalls, right? Right. So so-called syscalls. So-called syscalls, and you build your program on top of libc, right? You build your program on top of libc, and your program is executed from bash or shell. It doesn't really matter. So you have your program, libc, and libc interacts with the Linux kernel using syscalls. So Porth right now, let's actually say something like this: your C program. Your C program. So your Porth program cannot do it this way, right? It cannot do it this way. We have to interact directly without libc. So your Porth program is going to be something like this, right? So we have to use syscalls directly. Usually, quite usually, a lot of Linux syscalls have a corresponding function in libc. Right. So for instance, there is a Posix function read and write, and there's literally corresponding syscalls to the Linux kernel that are called read and write, and they have literally the same signatures and stuff like that. Right. So, but it's not really the case for the sig action, right? It's not really the case the sig action. So the actual syscalls behind sig action are slightly different. And by the way, the reason why the entire sort of like architecture is organized like this is because if something changes between the libc and Linux, right, the user programs will never notice that. If some of the syscalls will start to have like backward incompatible changes, all of your C programs will still work. So that's kind of the point. libc sort of like acts like a protective layer from any backward incompatible changes, right? So that's what it is. And it's kind of similar on Windows actually. So if this is on Linux, on Windows you usually have like a Windows NT kernel, right? Kernel. And here you have Win32 API library. I don't know what it is actually, right? So Win API library, and you usually cannot even directly interact with Windows NT like syscalls. You can try, but they change way more often than the Linux syscalls, right? They change way more often, and you're supposed to use the Win32 API library. But I'm not a Windows developer, so I don't know for sure. But on Linux, this sort of protective layer is basically libc usually. Right, it is usually libc. Yeah, and as Gia says, we can at least inspect the source code of Linux if we don't understand something, right? If we don't understand something on Windows, the only thing we can bet on is MSDN, and it's not, you know, sometimes it's not full. So you kind of have to use the DLLs provided. Yeah, you have to use that. As far as I know, people tried to sort of document the syscalls of Windows, like a reverse engineer, and like put some sort of like database of them. But I don't know how useful it is, actually. So I think we've got some subs. Thank you so much, Philippe Fontana, for 2 months of tier 1 subscription. Just because your videos at YouTube helps me a lot. Kisses. Thank you so much. I'm really glad that my videos help somebody and inspire people to do things. Hello everyone. On Windows, you just can't interface with the kernel that easily. As far as I know, if you like program in assembly, you can just issue a syscall instruction and it will work if the syscall is correct, right? It's just like you cannot rely on that, right? So it's not particularly reliable because in the next Windows update, they can change that, right? Easily without any warnings because it's like sort of internal API. Beanbear18, thank you so much for 4 months of Twitch Prime subscription. Thank you, thank you, thank you. Okay, so as I already said, we don't have that protective layer in Porth yet, and I'm not sure how exactly that protective layer is going to work. Right, but essentially, on Linux, the corresponding syscall is not really called sigaction, it is called RT-sigaction, and it has a slightly different signature. So there's a command called strace, which allows you to basically run the program and trace what syscalls it performs, which could be really useful. So let's actually run this command and see what syscalls it performs. Right, it performs some maps, probably done by libc to allocate some memory or pre-allocate some memory protections. And there you go, we have a RT syscall, but it also accepts sigint. It also, as you can see, accepts the structure with SA handler and stuff like that. And we can't see stuff very easily, right? But the thing about RT sigaction is that it doesn't accept 3 arguments as sigaction. As you can see here, we accept the signal, we accept the structure, another structure, and nothing else. Here we also accept the 4th argument, which is some sort of a number. In fact, we can actually go to Linux syscalls. Let's actually find Linux syscalls. So this is a Chromium S. Now I have to do 2 clicks. Maybe I should save that to bookmarks or somewhere. Maybe I already have that in bookmarks, but I'm too lazy. I'm sorry. And let's find RT syscall. Oh, not syscall. RT sigaction. So I hope this is the right architecture. Okay, so this is the right architecture, and here it is. So here's the 4 arguments. It's also pointers to some sort of sigaction structure. Right, and also it accepts some sort of a size. Right, it also accepts some sort of a size. And as I already said, we can actually look up what this syscall is doing by just downloading Linux kernel. Should we try to do that? We can try to do that actually. So I can grab maybe my kernel version. As you can see, it's a very fresh kernel. Kernel.org. Let's actually go to kernel.org. Is it still TLS? It is still TLS actually. Okay, so I can actually just download that. So I'm using something that is not that outdated, right? It is not that outdated. So let me just go ahead and do it like that, hopefully. Okay, we're downloading the Linux kernel. Since syscalls are code, probably done in assembly, why could I not directly make those yasm instructions instead of using the corresponding syscall? I don't really understand what you mean, because syscall is literally an assembly instruction. In x86-64, there is literally an instruction called syscall. It is an assembly instruction. And what this instruction does, it invokes an OS system call handler at privilege level 0. And I guess the answer why can't you just do it yourself is that you don't have enough privilege. And the only sort of code that have enough privilege is the operating system code, so you have to ask operating system to do something while issuing a syscall. Does that answer your question? Because I'm not sure if I fully understood your question. So yeah, it works at ring 0, and syscall is basically jumping to ring 0 to and asking operating system to do that. Hi, I have no idea how OS and DLL stuff works. How can the kernel with syscall change and the program still works? Quite easily, right? Imagine that you have a function foo, and you wrote a program that uses function foo. If you never touch function foo, your program doesn't break. Now, function foo may call function bar, right? your program still works because it doesn't call function bar directly. Now imagine we change foo to call buzz instead of bar. Your program still works because it doesn't know anything about the internal implementation of foo. It doesn't know anything about bar. It doesn't know anything about buzz. So the same mechanism works in Windows. You use DLL library, but you don't use syscalls. And the DLL library can change its internal implementation however it wants. The same principle applies there as well, right? So you just have a program that uses foo and you don't care what foo calls. It doesn't matter. Your program doesn't break, right? You call bar, your program still works. You call buzz, your program still works because your program doesn't know anything about bar and buzz. No, layer of abstraction. A simple layer of abstraction. That's how it works. Hey, I'd like to create a competing compiler for port at some point in time as part of my college class. Do you have an ETA on when the design might be finished? No, I don't have an ETA. And in fact, you can do a competing compiler for ports right here, right now. You can make the competing compiler for the code that is currently open. So, look. You can grab the source code that is available in this repo, by the way. So some people say that I closed the source code. I didn't close the source code. All of the 1,188 commits are still there. They're still there. You can download this entire thing, and there is an instruction how to access the last available version. And you can use whatever you have in that repo. So I'm gonna actually give you the link in here. Feel free right here, right now, to implement an alternative implementation for this compiler available in here. I'm totally okay with that. I'm totally okay with that. You can do that right here and right now. You can do whatever you want with the available code. Whatever is available, you can use that. But there will be a compiler for an outdated version, yes. And I'd like to do it for a new one. Then you will have to wait. And ATA, I don't have a ETA, I'm really sorry. It is ready when it's ready. But if you just need something for the college, you can just use whatever is available, right? So you just need something for the college. Okay, you're welcome. I'll try my best to finish with the design as soon as possible. Seriously, I'm working really hard, but there's so much stuff I would like to finish before I open it up. Like, there's so much stuff that needs to be done. I'm really sorry that I had to do that. But it's in, okay. So just a second. I already said Binber18, thank you so much for Twitch Prime, and I'm a whale. Thank you so much for tier 1 subscription. Thank you. Why do you need to implement Porth specifically anyway? Just implement your own stack-based language and borrow some ideas. Exactly. That's exactly the question that I keep asking myself. Why people want to implement specifically Porth? Like character to character. What's up with that? Because you could have just like implement a stack-based language that is like Porth, but not an exact copy of Porth. Like, what's up with that? I still fail to understand. Because it is not that hard. It's just like, don't steal the homework, make a little modifications. It's just like, I don't understand. If I saw someone's language that I really liked and I liked some of the ideas, the last thing that would cross my mind is to make an exact copy of this language. This would be the last idea. My first idea would be, wow, it's cool ideas. I'm gonna steal those ideas for my language. And I really fail to understand that. So anyway, maybe I'm just dumb. I'm sorry. So okay. So yeah, we already downloaded the source code. We want you to take a look at the Linux kernel. Okay, so let's do tar frex. As far as I know, Linux generates has a lot of files, so I'm gonna redirect all of the output to def null. All right. So yeah, it's taking some time. Linux kernel has a lot of files. What do you keep in your port folder? This? Okay. So let's go into Linux, and I'm gonna try to search for the syscalls. Hopefully I'll find the right place. Okay. So I'm gonna do some signal. I think it's just signal. Yeah, we're gonna go like this. Find type file name, and let's see what we've got. And that didn't work probably because I have to do something like this. Excuse me? Maybe sig action? Am I an idiot? I think I am an idiot. Right. Oh, there we go. So, okay, cool. x86 64 is just x86, and there is a signal. Okay, so let's go there. Hopefully I'm going in the right place. And can we find rt sig action? Right, so it's not available in there specifically. So maybe I can just grab rn sig action, maybe rt sig action. And what do we have in there? So there's not that many places. So there is a MIPS, there's some other stuff. Yeah, there we go. Signal.c. Okay, cool. So this is the syscall, right? And it accepts pretty much the same arguments. So there's some sort of a macro. I don't really know what this macro does, but I would assume that it defines a syscall with 4 arguments, right? So I'm not the only one who basically created like a syscall 1, syscall 2, syscall 3, syscall 4 for different, amount of arguments. Linux kernel, the Linux developers themselves did a similar thing. I remember how people didn't like that they create like intrinsics syscall 0, syscall 1, syscall 2, syscall 3. The Linux kernel developers did a similar thing with macros. So there you go. And here is this syscall that they're using. So you accept the signal, then you accept the structure for the action and the old action, and the 4th argument is a sig set size. And we can just check out how it is used. It is used to check whether it's equal to the size of sig set. I don't really know what is equal, but essentially you can kind of just assume on x86 64 that this value has to be always 8. Right, this value always has to be 8, and if it's not 8 for 64 bits, it's just gonna always reject this entire thing anyway. Right, so we don't have to worry about that. But apart from that, it is actually equivalent. It is actually equivalent to the sig action in here. Right, which means we can probably use this syscall directly. So let's go ahead and do that. Let's actually try to code in assembler. Right, in assembly. Assembler is a program that translates assembly language into instructions. Let's write a simple assembly program that uses this syscall to set up the, the handler and try to handle things. Okay, so let's go ahead. So let's do sig action.yasm, and we're gonna be using, I think today I'm gonna be using yasm, right? Have you guys heard about yasm? I think somebody suggested in the chat this compiler, and I looked into that compiler, and it is freaking amazing, actually. It's like, it's basically a better yasm. So it's a rewrite of yasm, right? And it's a better, so as you can see, the assembly developers also competing with each other, right? So, but they're competing with more or less like established notation or whatnot. Better than yasm, yeah. So I really recommend to check it out. It's actually pretty cool. So I actually brought back the yasm format for Porth, and look how quickly yasm actually builds everything. Just a second. Right, if I do Porth and I compile Porth.Porth, and the format is going to be yasm. So it takes almost a second for yasm to finish. Right, as far as I know, yasm took like 5 seconds to compile Porth. Right, it took 5 seconds. It's not as fast as phasm, and on top of that, I'm actually also including the the debug informations. I actually brought back yasm just in case I will need to debug the compiler, right? So because I can just include debug information with yasm, as you can see, and then just do some stuff like gdb, right, like that. And then I can break on start and run the program, and there you go. I have the debugger for the compiler, and I can just like do next and just like call things and whatnot, which is rather convenient. All right, unfortunately phasm does not allow me to do this kind of stuff. All right, so thank you so much Rick Says for Twitch Prime subscription. Thank you. And Knazer, thank you so much for 28 months of tier 1 subscription. Oh boy. All right. Is that the GDB inside of Emacs? Yes. All right, so sig action, and let's go ahead and do sig action.yasm, and we're gonna switch to 64-bit mode, right? So, and in here, I'll start a segment text. All right, and in a segment text, basically a segment text is the segment that holds the code of the program, right? So we're gonna have a global external symbol called start, and in a start we're gonna do some things, right? So that's very simple program. That is very simple program, and let's try to build this entire thing. So it's gonna be yasm f64 sig action.yasm, right? And that should produce the O file, right? That should produce the O file. And if I go to build sh, I'll be able to link the O file, sig action.o. All right, so let me see. Okay, so here's the sig action, and this is the program. And if I try to run this entire program, it is going to segfault, right? Because it's trying to return somewhere, but there's no return code on this stack, right? It basically returns nowhere. What we have to do, we have to issue an exit syscall, right? So the syscalls, if I remember correctly, they are. The number of the syscall is located in the racks. Okay, so we'll have to basically move sysexit in the racks, and I think I can just take the std Linux, right? So this is going to be sysexit, and it's 60. Okay, so let's actually define this thing somewhere here. So we're going to define 60 sysexit, and this is going to be 60. Right, so and then in the first argument, which is RDI, right, I'm going to set 0 and then issue the syscall, right? So as you can see, cschool is literally an instruction in x86-64. So I'm just putting some information into the register, and then I'm asking the operating system, please handle my request, right? And putting 60 into rex means I want to exit, right? I'm asking the operating system, I can't exit myself. Please unload me from memory, because I can't unload myself. I don't have enough permissions. I'm not running in a ring 0, right? So this is how it works. All right, so let's actually try to run it. As you can see, it exited successfully. And in fact, you can provide any exit code in here, right? And that's going to be the actual exit code that you exit with, right? So here is a 69, and here is the 69. Pretty straightforward. So thank you so much, LazyGrid, for 7 months of Tier 1 subscription. Thank you, thank you, thank you. And welcome back to our Epic Port Club. So there we go. So we have a simple program that can just exit. So, but we would like to have something that prints stuff on the screen. For that, we'll have to issue a write syscall, right? So rex syswrite. Let me take a look. Syswrite. So here is the syswrite, and I'm going to just put it in here. So this is going to be defined. Right. So, and the first argument of syswrite is the file where we write things, and in our case, it is going to be stdout, right? And if I remember correctly, stdout is simply 1, 0 is stdin, stdout is 1, and stderr is 2. Okay. So let's define stdout, and this is going to be 1. So the next argument, which is located in RSI, it's a pointer to the buffer that we want to print, right? So it's going to be RSI, and let's define some sort of a buffer. So we're going to allocate the buffer in a data segment, right? So, and it's going to allocate basically a string hello world, right? So I think this is how we do that, right? So, and in the third argument, right, we put the size of the buffer, right? So, and the size of the buffer can be computed using EQ macro. I think it is a macro, but essentially what it allows you to take your own address and subtract the buff address, and that is basically the size of this chunk of memory. Right, so here we set up the write syscall that will print this message, and we need to issue the syscall. There we go. So here we have a program that makes one single write syscall and one single exit syscall. As simple as that, it doesn't do anything else at all. So write has to be 1, I think. Yeah, this one. So let's actually try to run this entire thing. And as you can see, it says hello world and exit with exit code 69. Right, we can actually change that. Right, there we go. So it just exits normally and it says hello world. Cool. We can even use strace on this entire thing, right? So this is going to be strace, and in strace you will literally see that the only thing this thing does is executes 2 syscalls. The first syscall is write, and the second one is exit. There's also execve. I don't really know where this syscall coming from, probably from bash, but it's the syscall that basically oh yeah, I can see why, because bash forks itself and the child fork performs the execve to replace its own image. So this syscall is kind of a part of my program. That's actually very interesting. I never thought about that. The execve is actually issued by the child to replace its own image. Never thought about this one. This is actually very cool. So yeah, it's very interesting. All right, so, and to actually get a gist of how big, not really big, but what exactly the standard C library does, you can write an equivalent program in C, right? So we can do something like that, right? Printf hello world, right? And let's recompile the entire thing. Okay, and let's take a look. So here is program written in C, right? So this is a program written in C, and this is a program written in assembly. There is no differences between them, like visual differences whatsoever. But if you take a look at how many syscalls assembly program issues, it literally issues 3 of them, right? But if we take a look at the hello world written in C, and take a look at how many syscall it issues, this is how many syscalls it issues. Not that many though, a lot of program issues more, but it does a lot of things, and all of that stuff is done by the libc runtime. Just to get an idea that like there is a lot of stuff that's going on behind your back when you're just like writing the hello world. Right, and all of that is not performed if you're using assembly, because you're performing everything yourself. And here is the stuff that libc does for you, right? It just loads up some dynamic libraries and just checks some files, opens the libc dynamically. The libc pre-allocates some, like maps some of the pages for probably for the malloc, right? So closes, opens some files, like does a lot of stuff, and finally it issues write at some point and exits. None of that is really needed, but it just does that in advance just in case, right? It doesn't really add too much of the bloat to your program, right? It's just like something that is there that probably you want to be aware, maybe not. Not saying that whatever the C program is doing is bad, it's just like it's doing that. I'm just stating the fact. I wonder how many syscalls libc does when optimizations are turned on. We can actually check that, why not? Sure. It kind of derails the entire thing, the entire stream, but we can do that. Sure. Sounds like fun. Main as trace, and it does the same amount of syscalls. I don't think optimizer actually optimizes too much stuff. Right. Anyway, so Hey, Alan, thank you so much for Twitch Prime subscription. Thank you. Your first subscription, by the way. Alrighty, so let's take a look at SIG action. The next thing we want to do, we probably want to issue the, we want to create the signal handler, right? The same way we did that in a C program, right? So we have a signal handler, right? So here it is, and it says code a signal, right? Let's do the same thing. I'm going to allocate it in here. I'm going to call it a handler, right? And I'm going to just return from it now. But I also want to write something. So let's issue a write syscall inside of the handler, but write a special message. Let's call it something like handler message, right? So this is going to be handler message, handler MCG. Right, and the handler MCG is going to be something like, let's say, we're going to set up the signal for SIGINT, which is usually issued by Control-C. So let's actually say Control plus C, right? So this is going to be that. And the message size is going to be EQE, like minus this entire thing. Minus this entire thing. All right, so, and that's basically it. Right, so, and I'm gonna just try to call this handler to confirm that it actually prints what I expect it to print. So we're gonna do call handler, and let's just go ahead and run it, sig action. There we go, and as you can see, it prints Control plus. Cool. So let's try to call rt sig action, linux.porth. So sys rt sig action, right? Its number is 13. Its number is 13. So let's define it in here. So that means in here, what I have to do is move sys rt sig action, and the first argument of rt sig action is going to be the signal SIGINT. Right, so what's the, it's RDI. Okay, so move RDI, SIGINT. And the question is, what SIGINT is equal to? I don't really remember, to be fair. So let's actually go to C program and steal that from the C program. I'm going to maybe write an alternative thing in here. Right, and let's just print something like define SIGINT d SIGINT. Right, so we're gonna return from 0. Do I have a return in here? Yes, I do. Cool. And then I'm gonna rebuild the entire stuff and just do main expected Yeah, so let's comment it out. Okay, so sigint is supposed to be equal to 2, and let me just put it in here. Right. Cool. Yeah, everything compiles. So the next argument is in RSI, and we have to give the pointer to a structure. All right, so this is getting interesting. This is actually getting interesting. So, okay. We need to know the size of the sig action structure, right? We need to know the size of sig action structure. We can go ahead and just pre-allocate this thing, right? Like this. And I want to just print it. So let's define something like size, sig action, let's put it like this, size, 0, right? Size of assay. Size of assay, and let's just run it, and this is 152. Cool. It is in fact 152, and we need to allocate this exact amount of bytes somewhere. We can allocate it in data, but I think I'm going to allocate it in BSS. Right, so BSS is basically a section where all the stuff is initialized with zeros, right? So we can just do something like assay, and you can reserve the sig action size amount of bytes, right? Sig action size amount of bytes. Cool. So we basically pre-allocated the structure in the static memory, right? And now I'm gonna give the pointer to that structure in RSI. So it's gonna be assay. So this is RSI, and the next argument is supposed to accept the pointer to the old structure. We don't really care about the old structure, right? RDX. So we're gonna put 0 in here, so I'm gonna just put 0 in here. So cool kids these days actually do something like Zor in Dix, right? Zor in Dix. Don't Zor, okay. So, and right, and the last argument in here is going to be the size of sig set. As already established, it has to be 8, if I remember correctly. So it is R10, right? So it's going to be R10, and let's actually put 8 in here. So, and that will perform the sig action cschool, right? So, but it can actually fail, right? From the cschool in here. So the result of the syscall is returned via the rex register, right? So via the rex register. So if it's negative, right? If it's negative, that means the this thing didn't succeed. So let's do the following thing. Let's actually compare rex and 0, and if it's less than 0, we're gonna jump to failed sig action failed, right? Sig action failed. Something like this. And sig action failed is going to be like a separate handler in here, right? That will just print the error message, right? It will just print the error message. So what kind of error message it is going to print? So I need to take the right syscall and let's put it in here. So let's say that we're going to have sig action failed message, right? So this is a sig action failed message, and the message is going to be failed to set up sig action for whatever reason. There we go. So I'm not going to print the reason or anything like that because it will overcomplicate the code, and we're writing an assembly, so it doesn't really matter. So this is going to be the size, and what I just do is EQ to this entire thing. EQ to this entire thing. All right, so, and after that, I suppose we want to exit right? After that, we probably want to just exit with maybe, I don't know, with 1, right? To indicate that sig action failed. Okay, let's try to compile this entire thing and see if it compiles. Right, it seems to be compiling. So as far as I know, the sig action has to fail if this argument is not 8. Let's actually say that it's 9 and hope that it's gonna fail, right? So I'm gonna just do that, sig action, and as you can see, failed to set up sig action for whatever reason. Okay, so now if I put 8 in here, it actually succeeded. Right, but it didn't print anything, so I think it should print something afterwards. So we have a message, let's print OK, and this one is going to be just OK, like so. And let me take this thing, right, let me take this thing, and let me put this stuff in here. So this is going to be handler mcg, this is OK. OK, so buffer is not found, oh yeah, this is because it has to be OK. There we go. So as you can see, it prints OK. It prints OK if the cschool didn't fail, and if it fails, it will print that sig action failed, right? So everything. Might as well actually put something like error in here to make it more obvious, because sometimes it is not obvious, right? Failed to set up sig action for whatever reason. Cool. Nice. So we're setting ourselves for success. But again, we also need to wait for the user input, so we'll also have to issue the read syscall as well, right? Before we print OK, let's actually do something like move rex sys read. We're going to be reading from the standard input, and we're going to be reading into some sort of a buffer, right? So RSI buffer, and RDX is going to be buffer size. We're going to be reading into that one. Okay, and the buffer, I don't know what's going to be the buffer, so maybe I'm going to put the buffer in here somewhere. So it's going to be buffer db 256, buffer size. Though, can I just say buffer size EQ 256 and then use buffer size like this? I should be able to, I'm pretty sure. It should be possible to do something like that. Right, and let me just recompile the entire thing. Symbol sysread is not available. Okay, so let's actually grab it from here. Sysread. Alright, so this is a sysread. Define like so. And stdin. Okay, so we also need to define stdin. I think it's gonna be 0, right? And we also have a warning, value not fit in 8-bit. Because it has to be resb. There we go, cool. So now I probably can go ahead and try to run sig action. Fail to set up. Okay, so that makes sense. Because I need to set this thing to 8. Right, and then run it again. And it says okay, but it didn't wait for the input, which is rather because I didn't issue a syscall. Right, so that's why you should never program in assembly, because you can forget one instruction and the computer will not explain you things. Assembly scare. Assembly, yeah, scary. Assembly scare. Okay, so it's waiting for the user input, and if I just provide the input, it says okay. So as you can see, it's more or less equivalent to what we had in C. Right, so the time has come to actually start handling Control C. As you can see, if I press Control C, it doesn't print, you know, Control plus C that it's supposed to print, right? So it doesn't do that, which is a little bit sad, not gonna lie. So we just need to set the handler. I think I want to make a small break. I want to refill my cup of water, maybe even make a cup of tea, because I didn't make a cup of tea before and I'm kind of regret that. So yeah, let's make a small break, and after the small break we're going to continue working on this assembly demo. Okay, so let's continue. What I was doing, I don't remember. So I think I was setting up, okay, so we need to know the offsets for the different fields and stuff like that. So here, as you can see, we set up the handler, right? So we set up the handler, and we need to know the offset for the handler. So let's actually go ahead and just figure it out. So we already have that. So I think I'm going to do something like printf, and let's define sig action handler offset is going to be ZU, and this one is going to be offset of struct sig action SA handler. Right, there we go. So this is going to be that. And I'm going to try to rebuild this one, and offset of is not defined. I think you have to basically put that somewhere here in the definition. Okay, so let me try to run the main, right? Let me try to run the main, and the offset is literally 0, so it's located as the first sort of argument in there, as the first argument, and let's actually put it in here. So the function pointers in x86-64 are 64 bits, so we'll keep that in mind. So right before issuing the RT-sig action syscalls, let's actually put some stuff into the structure. So I'm going to move SA plus the offset sig action handler offset, and what I'm going to move in there, I'm going to just move the pointer to the handler, right? So this is going to be just the handler. And that should be theoretically it to set up the entire stuff, right? So we're basically translating the C code into the assembly code, right? So, well, in C code we're using libc function, but in assembly we are using the RT sig action syscall, right? Because we don't have a libc. We could have libc, we could link it, but it's not really an option right now for Porth, and we're trying to just research this kind of stuff for Porth. And let's actually try to run this entire thing. Okay, so invalid size for the operand 1, and I have to specify that it has to be 64-bit. What is it? 64? So word is 2, double word is 4, quad word, it's a keyword, right? So 64. Okay, so it is waiting, and if I press Ctrl-C, it segfaults. It does in fact segfaults. It doesn't really handle Ctrl-C the same way the C program handles, right? So if we go into here, let's actually enable the C program back, right? So I'm going to put it like that. So here's the C program that sets up the sig action via the libc, right? And let me actually do something like this. Let me not run the program after I rebuild it. Right, if I do something like that, I press Ctrl-C, it says code a signal 2. To reduce the amount of discrepancies, let's also say Ctrl+C, right? Ctrl+C, all right, and let's actually put this in here, right? And if I press Ctrl-C, it says Ctrl-C, okay, but if I do sig action, it just segfaults. So clearly, we're doing something wrong. We can try to figure out by actually s-tracing the sig action and seeing the differences between what we have in a C program and an assembly program, right? So we can do something like s-trace sig action. So, and that is basically the sig action that we are issuing. So let's actually save it in some sort of a buffer, right? So this is an assembly version, right? So we have a SA handler, we have some like empty mask, empty flags, null, and 8, right? So that's the syscall we issued. Right, and if we take a look at the main now, can we spot any differences? Okay, so that's a lot of stuff in here. Let me actually just quickly copy paste. So this is what we have in C, and that is quite different. That is actually quite different. So here we have sig int, so this is assembly, and this is C, rather libc. So this is what libc does. Right, so it has its own handler and stuff like that. SA mask is empty, but also SA flags, SA restorer, and there's some sort of a restorer in here. So we never actually explicitly specified any restorer, but the libc actually specified one for us. So, and this is basically the thing that libc hides from us. You remember how I said if something changes in the syscalls, libc is going to protect us from that. So essentially that's what's happening in here. So libc basically abstracted away from us, setting up something that is called restorer. Right, and if we take a look at the sig action, right, and by the way, so I think I should go without saying that whatever we do here shouldn't be done for like actual production software, right? If you want to write like a C program, just link with the libc and use whatever libc provides for you. Here we're trying to explore how all of that works on a deeper level, so that voids any warranties put by the libc, and you have to be aware of that, right? So you do guys realize that I do not suggest to program in production like that. What we're doing in here, we're just having fun. We're just taking apart the system and looking at the system and seeing how the system works, right? Does that make sense? Right. So this is not how you're supposed to write things, like it's like the opposite of that. And I'm doing that to research this stuff for my own programming language and just to see what fits better for my own programming language. Would it be better to implement my own layer on top of Linux syscalls, or would it be better to link with C? I don't know. I want to figure it out. I want to check it. So, and that's why I'm doing that. I'm just taking apart systems and look how they work. Okay. Whew. All right. So, and as you can see, it does provide the restorer, right? So let's actually search for the restorer. What does it say about restorer? Assay restorer field is not intended for application use. Posix does not specify an assay restorer field. Some further details on the purpose of this field can be found in sig return. Okay, so let's take a look at the sig return. Right, so sig return, RT sig return is yet another syscall, right? So if the Linux kernel determines that unblocked signal is pending for a process, then at the next transition back the user mode in that process, it creates a new frame on the user space stack when it saves various blah 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 blah. So anyway, essentially, restorer is basically another function that you have to provide for this entire thing to work properly, right? So let's actually just go ahead and do that. And on top of that, if you have to provide the restorer, you also have to set the flags that you provided the restorer. So this is the two things that we'll have to do, right? So let's go into the assembly code, sig action yasm, and we have a handler in here, and we're gonna have some sort of a restorer. Right, so this is going to be restorer, and let's issue the message that we are in the restorer. Right, let's have something like restorer message, restorer. Right, so we have a handler, and let's have a restorer. Restorer, and what we're going to say in the restorer: I am a restorer. I don't know. So I am a restorer, basically. Cool. So let's actually set a restorer, offset restorer, like this. But we need to know the offset itself. So let's go into the main.c. Right, and let's set the restorer. Restorer. There we go. So let me just build the entire thing. And sig action restorer, so I have to put something in here. I don't know what exactly I'm going to put in here. Right, but yeah. And let's start the main. I didn't want to start the main, so I need to switch back to my other main in here. So I might as well maybe put some sort of if condition in here. So let's say if one, otherwise that way I should be able to quite easily switch between two mains. Like if it's 0, it's going to be using this main. If it's 1, it's going to be using this main, right? So, and let's go ahead and try to do that. So here's the offset for the restorer. It's actually far away from the beginning of the entire structure. It's pretty far away. Right, so, and let's put it in here. Right, so this is the restorer. Does it compile? It seems to be compiling. So another offset that I need in here is the offset for the flags, right? So this is going to be flags. Let's take a look at them. And the flags are located at 136, right? They are in fact located at 136. Okay, so, and as far as I know, the size of the flags, right. So we have to be aware of what the size of the flags. Size of flags is going to be ZU. Size of assay flags. Size of assay flags. It's actually 4, so it's 32-bit integer, so you have to be really aware of that. Okay, now let's go ahead and set that flag. So it's going to be move keyword SA plus sig action flags offset, and we have to set SA restorer in here. So, but we don't have a restorer, and as far as I know, you can't access the restorer from C because it's an internal libc library. dword, dword. Thank you so much. So it's a dword. So it's an internal thing. We can try to do that, right? So it's going to be define SA restorer. And I'm going to put a value in here, SA restorer. There we go. So SA restorer, as you can see, you can't really access this stuff. And usually for this kind of stuff, I go into Musel, which is basically a libc library, implementation for a libc library. And it's pretty simple one. I really recommend to check it out. And let's actually take a look at it. So this is Musel. It actually has to be capitalized like this. All right, so I think I have it somewhere in my third-party thing. And let me grab define SA restorer. So will we be able to find something? So on x86-64, its value is equal to that, right? Its value is equal to that, and let's just put it in here. Yeah, let's put it in here. So this is going to be defined, and that should be enough, I think. Right, so if I try to now recompile the entire thing, so it's going to be build.sh, SA restorer, yeah, so we don't have that in C, so let me remove that. And now, if I try to do sig int, sig action, I press Ctrl C, it still says segmentation fault. Right, so let's actually see that we didn't make any mistakes in here. Right, so here is the return. So maybe I want to put the return here as well. So everything should be fine. We set up everything. So the structure is zero initialized and everything. So I don't see any problems in here. Right. So let's try to do strace on this entire stuff. Can you spot something weird? Can you spot anything weird with this strace? Where are the SA restorer and SA flags that we just set up? No flags are set up and no restorer are set up. Something is really weird going on in here. Even though we got all of the offsets of the structure, right, we got them from the libc, and we put them in there, we used those offsets, we pre-allocated the structure of the required size, and we just didn't get there. Like it says that flags are not set, nothing is correct. So what could be up with that? Does anybody know? Well, what's up with that? Like it's just like it's kind of weird. And the answer is pretty annoying. The answer is absolutely annoying. You won't believe how annoying it is. So let me see sig action. Sig action. So the structure sig action that is used by libc library is not the same that is used by the kernel. And it took me way too much time to figure that out. So this structure and this structure are different structures with different sizes and different offsets. Yes. And that was fucking painful to realize. This is the most painful thing. So you can't just use the libc structure, right? You have to use the kernel one. In fact, libc translates the libc structure into the kernel one before issuing a cisco. So we can even see that in Musel, in fact. So if you just search for RT sig action, right? RT sig action, and here is the implementation of RT sig action, I think. yeah, it's a wrapper. So libc sig action, which calls into the RT sig action. So this is the source code of Musel. So what they do in here, right? So they have two structures, SA and key SA, right? SA is whatever the user has provided. So here is SA, and KSA is the kernel one. And as you can see, they basically first translate, they reassign the values from the libc structure into the kernel one, and they're given the pointer to the kernel one. That's what they're doing. And also they're by default setting up the restorer silently. You didn't sub the restorer, as you can see, they're setting it up. So they're literally doing that, which is rather interesting. Furthermore, you can actually search for restore RT. You can search for what they're setting it to, and it's also quite interesting. It is in fact very, very interesting. So let's actually search for restore RT, and you may notice a very interesting thing. All of the restore RTs, all of the default restorers by the Musel are in assembly. They're not written in C. They are written in assembly. And what they do, they just call back with sig return, right? So they just issue that sig return syscall that we saw, right? But they all are written in assembly, and there's a very good reason for that, and there is a very subtle reason for that that we'll get into a little bit later. So in any case, before we go any further, we need to figure out what is the kernel structure, right? So what is the kernel structure in there? So let's actually find, as far as I know, in Musel it's just called K sig action, right? So here it is, x86 64. So here it is. So this is the kernel structure. So it's pretty tight. It's pretty small, in fact, and you can literally copy paste it into the C program if you want to, and just figure out all of the needed offsets, right? So let's put it in here. So in here, instead of like sig action, we're going to be using the K sig action. Let me see. So it's K, and for that one, it is also going to be K sig action, and that should be it essentially. So let's actually try to run main. Right. So what do we have in here? Uni std something offset off. I don't quite understand. Has no member sig action handler. Oh boy, what do you want from me? K sig action. Oh, because it's not called SA handler. I see. It's just called handler. Or flags or restorer or anything like that. There we go. So the actual size of sig action structure is 32 bytes. The offset for the handler is 0. The offset for the flags is 8, and the offset for the restorer is 16, even though the size of flags is... Oh, that's very interesting. The size of flags is actually 8. So it's not 32 bits, it's actually 64 bits, right? Okay, so let's actually copy paste the new offsets. Copy paste the new offsets. Sig action yasm. So let's put it like this, and I think that is basically going to be it. Except here we'll have to use keyword, right? So let's just use a keyword, and let's recompile everything. So hopefully that will work. And now, if I do sig action, I can press Ctrl C. It said Ctrl plus C, then I'm a restorer, and then sig faulted. So it kind of worked, but it still touched the memory in an appropriate place anyway. So, and if we take a look at strace, right, it issues the correct syscall. So it sets the flag, it sets the restorer, and stuff like that. So we have some sort of a progress. And here is an interesting thing, right? So here is the handler, and here is the restorer, right? So in a handler we print Ctrl plus C. And in a restorer, we print I am a restorer, I think. Restorer, like that. So essentially, when we pressed Ctrl C, first a handler was called, then we returned from handler, and then restorer was called, we printed the restorer, and then we returned from the restorer, and somewhere after that, we went to inappropriate place in the memory and something like completely crashed. So essentially, what you have to do in a restore, you instead of returning from the restore, you have to call sig return. Right. So in a handler, you have to just return from the handler, but for the restorer, you have to call sig return. Right. So, and the reason why it is like that is that because before calling a handler, I think the kernel adds to the user stack additional information about the issued signal, right? So it puts some sort of trampoline or some, like it just puts some section. And you need a special syscall to clean that up, right? And the restore is basically the place where you do that, right? It's the place where you do that. So we're gonna issue write, and then we have to issue the sig return. So we have to do rex sys rt sig return. And as far as I know, on x86-64, sig return doesn't really accept any arguments. You can just do syscall, right? You can just do something like that, and that's gonna be fine. Right. So, but we need to have the sig return. So let's put it somewhere here. So this is the sig action, define sig return, and let's try to recompile the entire thing. It is recompiling, and if we press that, everything's fine. Let's actually do that without a trace. Okay, cool, look. It was waiting for the input, Control plus C, then I'm a restorer, and then okay. So it is, this is basically the correct way. This is basically the correct way of setting up a signal on x86-64 Linux from assembly without using libc. That's how you essentially do that. And it is not obvious because it is not properly documented anywhere, because you're not supposed to be doing it like that. You're supposed to be linking with libc and just like use whatever libc developers provided to you, and let the libc developers and the kernel developers come up with the interface between each other over the pint of beer in a bar, right? Without philsip labs participating in the process of figuring out how the libc and the kernel has to talk to each other. So that's how it's supposed to be working. So the plebs have to just use libc, and the real developers just, you know, talk among themselves without writing any documentation. I'm joking, of course, it's all joke, it's not like that. But anyway, so it's not that bad actually. You have the source code. The source code is the documentation, right? So you can always just take the documentation of libc, take the source code of libc or the source code of the kernel and just figure that out yourself, right? You can just do that yourself. Isn't it great? I think it's pretty great. You can't do that to Porth, right? But you can do that to libc and Linux kernel. Is it actually possible to call RT sig return at the end of the handler and not defining any restorer? This is a very interesting question, actually. So the way it works, right? I think the way it works, because I'm not 100% sure, because I'm not invited into the secret club of libc and kernel developers, right? So it's actually pretty rare when you can go into such club. You can only read the source code. But I think this is how it works, right? So a signal is issued, and on the call stack, you have some sort of like info, right? So let's put it this way. I think it's going to be like 10 info about the signal, right? So this is what you have on the stack. And then on top of that, you have a return address, right? You have a return address. So, and with this state of the stack, you go into the handler, right? So you can't really access this info because it's behind the return address. So if you try to do that, you also will be getting the segmentation fault, right? So let's actually put it like this, right? And I'm going to recompile everything, right? And do sig action. I'm going to press Control C. You got Control plus C, but you got segmentation fault. Right, because sig return because sigreturn expects info about the signal. I think this is how it works. But in a way, there is a return address. So you have to first get rid of the return address. You have to get rid of it. The way you get rid of the return address is by returning from the handler. And here's an interesting thing. Where that return address is pointing to. Right. Think about it. It's actually one logical step. What is it pointing to that you have to return to get rid of it? It is pointing to restorer. Kernel literally takes this restorer address that you put into this structure and sets it up as a return address in a handler. So the next time you return from the handler, you in fact jump into restorer. And in a restorer, since you don't have a return address, you just have this info, right, which you can just clean up by sigreturn. So that's how it works. We can try to confirm that, actually. We can try to confirm that. So look, I'm going to rebuild everything, and we have a segfault. But we can remove that return address ourselves. What if we just do poprex? So it's on the stack, it's 8 bytes long. Let's just pop it. Let's just pop it. Will that help? Will that get rid of this entire thing? Right, it worked. But it didn't go into the restorer. Look, it literally didn't go into the restorer. It didn't. And what's funny is that it didn't segfault either, right? Because we didn't really have any return address. Oh, we didn't even have to, right? Because after the sig return, the kernel returned us back into where it was. So that's basically roughly how it works. I think, but I might be actually wrong, so please correct me if I'm wrong. Why is the return address there though? That's a good question. I have no idea. Like if restore doesn't have a return address to clean, why does the signal handler also not have a return address? I have no idea. So these are the questions I have no answer to. I can only show you how it works. Why it works this way? I have no idea. There's probably some weird like legacy reasons, or maybe there's some sort of like mechanisms that use all of that, and that is super important. Maybe it is needed to maintain the backward compatibility, in the sense that before the signal handlers had to just return from the call, and they didn't have to clean up anything. And at some point, you need to start cleaning up things. So to not rewrite some of the existing signal handlers, they decided to sort of reroute it. Okay, let's reroute the signal handlers into restorer who will actually clean up the return address. Maybe it was like that. Right. Yeah. So yes. Can you try it not to set the SA restore flag? Sure. And it segfaults. For whatever reason. It just segfaults. Probably because... You know what's interesting is that you must set up the restore flag, but you don't have to set up the restore address. Because you know what? The kernel doesn't give a shit whatever address you put in there. It will just put it as a return address for the handler. Seriously, it will just put it as a return address for the handler. And if you just put nothing in there, or in this case it's going to be 0, you will try to return from 0. Right, you will try to return from 0. As you can see, it will print control plus C, but then segfault because you try to return from 0. But that just means that you have to pop rex, which is 0 by the way, it is 0, and then you have to sig return, and that's going to work fine. So you don't even need to have the restorer as a function anyway. You just have to have something there, and you just have to discard that address. You can just discard it. It is very interesting. It is a very interesting mechanism. It is super fascinating. I love it. So that's how it works on Linux. I can imagine that on other Unix operating systems it works slightly differently. Right, but it's roughly like that. Anyway, so as far as I can understand, the supposed way of working with that, you just return from this function and you just like do it like this. And here is the reason, chat. Here is the reason why restorer in Musel and probably in all of the libc implementations is written in assembly and not libc, because restorer is expected to have only this info about the signal on the top of the stack. But the usual C function, according to the Linux x86-64 conventions, accepts the arguments via the racks and stuff like that, and it tries to prepare the stack and whatnot. It tries to mess with the stack in some weird way, and it also expects to have a return address on top of the stack. But restorer is a special function that doesn't have a return address on the top of the stack. So the usual C routines about preparing the usual preamble of the C function will just mess up this entire stuff. And that's why the restorers in Musel, for all of the architectures, are implemented in assembly, because it has to be just a plain jump into an address and an instant sig return call. You see? You see that? It's so fascinating. Like, you can't implement restorer in C. You just can't do that, because it has to be a very special thing that does a very special thing with the stack. You can only do that in assembly. Unless you're maybe using some undefined behavior in C, probably, but I mean, it's not going to be portable in any way. This is so interesting. Like, there's, I don't know, like, you may want to try to do that just to discover all of these interesting, weird things. Or maybe I'm just a nerd. But I find it so fascinating. Okay, so this is how this shit works. Can we implement that in Porth? Here's the very interesting, here's the real question, chat, for you. Can we implement that shit in Porth? So the question is how Porth functions work. Porth functions work in a very interesting way. So I probably, okay. In Porth, we don't have a single stack. We have two stacks. Right. So the first stack is called data stack, and this is where you push all of the operands, right? You push numbers and you push addresses, and this is where all of the operations are happening. So if you sum up numbers, they're summed up on the data stack, right? And another thing we have is a return address, return stack, return stack. So return stack, cool. And the return stack stores the return address when you call to a function. So when you call to a procedure, what's happening? Right, on x86-64 in Porth, we're using the usual stack, the usual call stack of x86-64 as the data stack. So that means if you call to a procedure, we'll get a return address on the stack. So the stack grows down, by the way. The top of the stack is going to be the last element. So once we enter the procedure, in Porth, we move the return address into the return stack to clean up the space for the input arguments. You may have some input arguments like A, B, and stuff like that, right? So after the procedure has finished, we return stack back into the data stack, and we issue ret instruction, which removes it from the data stack and returns back. So that's how usual lifetime of the procedure is happening in Porth, right? So, and because of that, we can try to implement a handler, right? So handler is going to probably have some, you know, info about the signal, right? The info, the signal info, and then it's gonna have a return address, which is gonna be restorer address on the stack, which we will move into the return stack, and then we'll return back into the restorer. So theoretically, like, we can just translate the assembly code into Porth, and it should kind of work, if you know what I mean, right? So it should kind of work. Let's actually give it a try. I think it's gonna be interesting. So far, like this is how Porth works, by the way. This is how procedure calls work in Porth. We have two stacks, and the movement of return address from the data stack into the return stack is x86-64 specific, right? So, like, an abstract Porth machine pushes the return stack, the return address into the return stack directly right away, but it's an abstract Porth machine. The specific implementation of x86-64 does that first on the data stack because it has no choice, right? So that's how it works. Does it make sense? We can even take a look at the source code of Porth. So it's somewhere in the generator. So if I take a look at op call, right? So what op call does, it just performs the call, and then it jumps to op prep procedure, and the op prep procedure pops the return address, the return address from the data stack, and moves it into the return stack. And R15 is pointing at the top of the return stack, right? So as you can see, we're just moving it there, and then we're allocating on the return stack like additional memory. So usually operand is equal to the amount of bytes of local memory to pre-allocate on the return stack. So you just pop drop the return address and make sig return. Not really, you can't access the return address in Porth directly. It is located on the return stack and you have no access to the return stack yet. Maybe you will in the future. Prep might not need to use rex. Okay, so people are jumping ahead of everything. So yeah, we'll talk about that. We'll talk about enabling or disabling this specific instruction in Porth because it's going to be interesting. So because that specific action may cause some problems when jumping into the restorer, right? So you're already getting the right logical steps, right? So yeah. So basically, the entire 2-hour stream was set up for this thing, right? It was basically an explanation for what we're gonna change in here. So it was just a setup. Punchline is pretty soon. Punchline is pretty soon. So let's first translate our code from assembly to Porth, right? Okay, massive. It's a massive build-up. Like that's why I decided to make it like a separate stream, because first I wanted to like make a short video. Then I look at how many logical steps you need to make to get there. I decided no, I'm gonna actually do like a whole stream because it's fucking interesting. Like I really like that, and that's why you should try to implement your own self-hosted language yourself, because it's fucking interesting. It is extremely interesting. Okay, so let's do sig action. I don't know, let's call it control-c.porth, right? And let's include the standard library, std-porth, proc, and hello world, and let's do puts. So this is the simple hello world in Porth. So let's try to compile ctrl-c Porth, and we don't have a standard library, but we can easily just say, okay, search for the standard library here, and there we go, we have a standard library. So you can actually you know, specify the path to the standard library, and it works. Then we can take a look at the generated assembly in here. It shouldn't be very big. It has a lot of strings. I think DCE should get rid of all of them, but it doesn't really matter that much. But yeah, we have a lot of stuff in here. So since we have DC, I should probably get rid of the print function because it's not really important now. All right, so now let me open the assembly that we are using, sig action yasm. You know what? I think I'm gonna take this line and I'm gonna put it into my build. So it's gonna be build.sh. I'm gonna have it in here. So we're building all of the necessary like programs to demonstrate all of that. Right, so this is gonna be build.sh, and let's take a look. Everything seems to be building. Right, so that's pretty cool. Okay, so let me open the sig action.yasm. And in here, we need to pre-allocate, we need to probably specify the, like this stuff, right? So let's do const size of SA action. Let's say action, sig action, and it has to be 32. Let me see. Do I have that specified? Okay, I don't have that in the standard library. So the next thing is gonna be sig action handler. Right, it's gonna be 0. Sig action restorer, which is 16, and sig action flags, which is 8. And also we need to have the SA restorer, and it's 16 hex, I mean, so that we'll have to translate it to decimal. Right, so const SA restorer, like that. So this is going to be hex. Cool. So that's what we have. And in here, let's set up the structure. So I'm going to pre-allocate this structure in local memory. So it's going to be SA size of sig action, right? And SA sig action handler, sig action handler. So we will need to specify the handler itself, right? So it's going to be proc handler, and in the handler we're going to just print control plus C puts. So a port is already more convenient than assembly, because you can just like specify inline the strings, which is super convenient, I think. Right, so yeah, programming language. So, and it's a handler, pointer plus. So you'll have to take the address of the handler, right, and save it into this specific field of this structure. And this structure, by the way, is not 0 initialized, so I probably want to do something like size of sig action, then 0, then SA and memset, right, and then drop, because memset returns the pointer to this thing. So this is the address. The next thing we want to do, we want to set up the flags. SA restorer, SA sig action flags, pointer plus, and we're saving just as a number. And we want to have the restorer as well. So let's have restorer, like so, and the restorer is supposed to print I am restorer, and then it's supposed to do RT sig return, and usually syscalls return the exit code. We're gonna drop that. Okay, there we go. So we set up this stuff, address of restorer. So this is gonna be restorer, sig action restorer, pointer plus, save the address. So we might as well actually maybe make it a little bit like shorter. It doesn't have to be this way, right? It could be just like that, and we can align by SA, which kind of worked almost, except it didn't. All right, like that. Then we can align by pointer. There we go. So that looks a little bit better. So as you can see, we just have a structure, SA structure, and we're just assigning all the fields in here. So it's pretty cool. Okay. So now we need to issue the sig action or sig action syscall. So let me just copy paste this thing. So the first thing we'll have to do, sig int, right? So this is a sig int. We'll have to do that in a reversed order, right? Because this is how port works. So it's going to be 8. Then we're going to put null. Then we're going to put SA. Then sig int, and then RT sig action. And after that, we may want to check. If that thing didn't fail, right? So if this thing is less than 0, we're going to say something like eputs error could not set up sig action for whatever reason, right? And we're going to exit with non-zero exit code. There we go. So we're going to have something like this. So after that, we are going to be reading from the user input, right? So we're going to be reading from the user input. So we'll need to pre-allocate some sort of a buffer. So let's do buffer capacity. Oh my god, I didn't mean to do that. And buffer capacity is going to be constant 256, right? So, and in here, it's going to be buffer capacity, the buffer and standard input, and we're just reading from that, and we're dropping the exit code, the return code, because we don't care. After that, we're gonna just print OK. right? We're just printing it OK. And that is basically the entire example, right? Except it's not going to compile because we don't have wrappers for the syscalls like sig return. So let's actually implement them. So it's going to be inline proc. It's not going to accept anything, but it's going to return integer. And in here we do sys_rt sig return syscall 0. There we go. And sig int, and I can just go to here. Sig int is 2. So let's define this constant in here. Like that. Sig action is a similar thing. We need to make a wrapper for that, inline proc. So it will accept an integer, then a pointer and pointer, and an integer, and return an integer. sys_rt sig action syscall 4. There we go. So that's what we have in here. Cool. So does it compile? It does compile. So we translated the assembly example to Porth. Right. So, and let's see if it's gonna work. It's rather interesting, right? So we have Control C, and it is waiting for the input. And let's press Control C. And this is something very interesting. We got Control C, then we got AMA restorer, and then we got a segmentation fault. Even though we did everything exactly as in assembly. We did everything exactly as in assembly. So the question is, what the hell has happened? What the hell has happened? Though it's rather interesting. It's rather interesting because we didn't get OK, right? We didn't get OK, so we didn't even reach this place. We didn't reach this place. So as already said, when you enter the procedure, it starts to mess with the stack. It pops racks. And when you jump to the restorer, right, you don't have a return address, you have the info on top of the stack. So jumping to the restorer is kind of dangerous in here. So you can easily resolve that by the trick that was suggested in the chat. Let's just include the restorer in here, right? So that should work, right? So that should kind of work. So restorer does not exist. We might as well, again, we can actually put a 0 in here, or we may not even set anything in here, because what we learned is that it just like puts whatever value you put in there. You only need the flag. You don't really care about like the actual return address. So we are dropping it anyway. And what's interesting is that when you do sig return, it's not gonna be problem anyway, right? So it will, the kernel will return for us. Right, it's the kernel that will return us from the handler. So let's go ahead and try to do that. Everything seems to be fine, and let's take a look at this thing. That worked. That actually worked beautifully. That worked more beautiful than I expected. So, and you know, that is extremely weird, because there's one last piece of puzzle that is not kind of resolved, right? It is not resolved. So when you go into the handler, right, you take the return address. You take the return address and move it into the return stack. Then you go into the sig return, and the return address that you put into the return stack is still there, right? Once you return back, you're gonna have the 0 return address in here, but that doesn't cause any problems. That's what's interesting in here. That doesn't cause even a single problem, but I feel like it should. Or maybe it shouldn't. Maybe it doesn't matter. So what if we have the actual restorer in here? So let's call it I'm a handler, right? And let's create a restorer. Just in case you want to have a restorer. And let's set it as the return address, right? So we're not going to use it, but we're going to set it as the return address. So just to see what's going to happen. And it still didn't cause any problems. So that is really weird. Oh yeah. So my point here is that after this return, the return stack of porth is going to be polluted, right? It is going to be polluted, right? It's going to have the value that it's not supposed to have, but it's there. And I wonder how can we confirm that? Because I would expect that value to be the value that you return to after the main, right? So you just return to after the main, but it just like doesn't really cause any problems. Maybe if I do echo and just take a look, it's 0. Very interesting. Very, very interesting. I think I know what I did last time when I actually encountered that problem. I think I know what I did. So I actually allocated all of these things not in a local memory, right? I allocated them not in a local memory, but rather in a temporary memory, and I used bindings for all of that. So let me show you. So you can actually rewrite these local memories like so. Right, you can take the sizes that you are allocating and you can do tmp alloc. All right, you do tmp alloc, then another tmp alloc, and you basically binding them like this. So this one is going to be SA, and this is going to be buffer, and this is equivalent code, in fact. Right, and then you can just like do it like that, and that pushes additional stuff onto the return stack. And this is where things can get messed up, I think, because then you'll have stuff on the return stack that you don't expect, and you expect this thing on the return stack. So it's going to be really, really, really fun, hopefully. So let me see. So hopefully it's going to produce the... No, still doesn't cause any problems. If you call a proc from main and do the stuff there, the 0 return would cause a seg fault, yeah. All right, I guess you can just do it like that. But my idea was actually to not... This is really interesting because I really would expect this thing to crash, right? Because after you return in here, you just must have some sort of a problem, but I don't have that problem anymore. Anyway, so yeah, I guess that's essentially it. We may want to have some sort of adjustment for the procedure. So essentially, what I want you to do, I want you to introduce some sort of like a no return procedure, right? Which basically does not store its return address on the return stack, right? Essentially, if you mark the procedure as no return, it will take its return address and throw it away, right? It's not going to put it into the return stack because you see what's going on here. I think I need to visualize that, right? So the problem that's happening in here is that when a handler is getting called, right, we have info on the stack, right? So the signal info, and the return address. Okay, and then temp2, right? So this is return stack. So then we move that return address in here, right? And then as we issue sig return will clean up the data stack, but the return address from the handler will stay in the return stack and will continue staying there after we returned after Control-C. You see what I mean in here? Right, so the fact that this procedure, like put that return address into the return stack still continue exist. This value still continues exist in here. So it sort of pollutes the return stack, right? If you don't throw it away. So what I was thinking is that we may introduce special no return functions that take their return address and just throw them away, right? And they never put them into the return stack, and you'll be able to use such no return function to put as a signal handler and make sure that it does not pollute the return stack. And what's cool is that this thing could be used also as a semantic indication for functions that never return, like exit function, or sig return syscall also never returns because it returns in a slightly different way. So it may have syntactical as well as semantical indications, right? For instance, it may forbid allocating memories, local memories in here, to not mess up the stack. It may be also used in the type checking, right? It may be also used for that code elimination. And on top of that, it also throws away the return address for this kind of stuff. Maybe sig return restores all the registers to reset R15. Maybe, actually. So that could be the case. I think I know what's happened. Okay, so I recently made a modification. Yeah. So yeah, I didn't realize. Thank you so much. Thank you so much for restoring the stuff. Oh yeah, maybe because of that we won't need this keyword anymore then. Yeah, we don't need it then. Yeah. Okay. So it probably restored. I'll need to confirm if it restores or not. So here's the thing. I think yesterday or the day before yesterday, instead of R15, I was using literally a memory to keep track of the top of the stack, right? There was like a pre-allocated section that was called a return stack RSP. And this was like an 8-byte chunk of memory that I used as R15. Right. So then I decided to do optimization and move that value into the register, into the dedicated register. Right. And I actually prepared for the stream while I was using this thing, and it was crashing it because it's a region of memory. And if the kernel restores the registers, of course it's not affected. Right. So that's why for me, when I was preparing for the stream, it was crashing, but it's not crashing anymore because now I'm using registers. Thank you so much for explanation. That actually makes a lot of sense. Right, so, and because of that, maybe it should become the part of the, of the semantic of the language. So you just can use a regular procedure and just sig return from it, and the kernel will just restore the registers and stuff like that. So, but I need to research that a little bit later. Thank you so much. So yeah, and this is how we can do the signal handling in Porth now, I suppose. But it requires a very specific code generation, apparently, which is very interesting. But yeah, so you can do control C and stuff. So you can do control C and just like exit and stuff like that. That is very cool. All right. So can we apply that to a real world? Why does a RT sig return signature have a return value of int if it never returns it? Because cschool 0 returns values always. And sig return, I think sig return can fail. Can it? Can it not? I think it can fail. Anyway, so let's actually try to apply it to a real world. So we have an example here. Oh my god. Okay. Which is basically the snake, right? So we have a snake game written in Porth. So here's a snake game. You can exit this game by pressing Ctrl C, right? Let's actually catch Ctrl C and don't let the player exit the game like that. Right. So essentially the only way to exit the game is going to be just by pressing Q. So let's just add that small little touch to the game. I think it's gonna be interesting. So this is gonna be like an actual use case for this feature. Maybe we'll encounter some problems along the way. We'll see. But for now, I'm gonna just like take this sig action related stuff and I'm gonna move it into the standard library. So it's gonna be std linux porth. There you go. And so let me open the example snake game, and what we're gonna have in here. So let's call this control. By the way, I'm programming in Porth, so that means I can literally call my procedure control plus C. I mean, you can. Oh, by the way, I also get the signal as an argument for this function, but since it's passed via rex, it's basically destroyed. Yeah. So we'll have to think about that. So maybe at some point I will make some external function that allow you to get that. So it's gonna be interesting. Okay, so this one is gonna be control plus C. All right, and in here we're gonna be just setting up the sig action. Right? So let's do memory, SA, and then we're gonna just set everything up like so. So it's gonna be simply like that. SA, sig action, handler. Right, so we're gonna do that. And instead of handler, I'm gonna do control plus C. I'm gonna not do that. Cool. Alright, so let's do a snake. And if I do control C, it actually... Oh, reading command has failed. Okay, that's cool. Well, I mean, that's very interesting. So I suppose reading command was interrupted. I think that's what happened. So I suppose if it's not E again, right, so return... Oh, this one is rather interesting, so I can probably do something like negate it. Then return E interrupt. Right. I suppose like this. Can I do something like that? Only then. So this is sort of like the errors from the read command that we expect. We expect either E again or E interrupted. Right. If it was interrupted, we can just try again. Who said we cannot? Yeah, let's just go ahead and try again. Okay. So can I now try to do that? And we don't have E interrupt. So let's go into the Linux. Right. So where are the errors? Const E inter. I think that's how we do that, but I need to have this. So let me print f const E inter. Is that how we spell it? I'm really not sure, but the compiler will always tell me. Too many questions. Okay, so what do you want from me? I just want to see the value, man. I'm so tired. Handler does not exist. Okay. Yeah. Sure. Come on. Restore does not exist. Doesn't matter. Okay, so the only thing I want in here is just to see what is that. Okay, thank you. It's 4. And in Linux, if I go to Linux, it is in fact 4. Alright, so everything's fine. If I try to run the snake, reading command has failed. Okay, so I probably fucked up the logic, right? So where did I fuck up the logic? It has to be end, right? Cool. I have to reset. Okay, so I'm gonna try to press Ctrl+C, and it still fails. Right, so you cannot just do it like that, so it still fails. So it probably doesn't return interrupted. So, and the question is, what does it exactly return? We can try to see that, because I'm really curious, like, what the hell is going on? So it's eputs return eput u. Right, so what does it fail with? I want to see that. It's failing with the negative value, so let's actually negate it. So what is it equal to? And it's equal to 5. What is 5? Does anyone know? So let's go to third-party musl thingy, and let's define E interrupt. Right. So it is probably generic EIO. So it's straight up IO error. So if I take a look at the read cisco, when does it issue EIO? This will happen, for example, when the process is in the background process group, tries to read from its controller terminal, and either it is ignoring the blocking sig T-ind or its process group is orphaned. It may also occur when it is a low-level IR when reading the disk or tape. A further possible cause for your own network file system. That is actually pretty serious. So I/O error. Okay, what if we just go ahead and ignore that error? I wonder what's gonna happen. So I'm gonna go into the Linux. So EIO, and this is gonna be 5, and on a snake, it's gonna be EIO. It's probably a bad idea to ignore that error, but why not? Why not give it a try? So Linux. Excuse me. Why are you saying redefinition? Oh, already had it. Okay, so already had it. Okay. Oh, that's fun. Well, I mean, it kind of worked. So, yeah. That is actually very interesting. And I can't kill it. But yeah. So it can't even handle the queue anymore. Right, it can't handle the queue anymore. Right, but I can kill it. Like, I tried to make it so I can't kill it, and now I can't kill it with Control-C. Like, I can't kill it at all. So one of the things we can do, I can just grab snake and kill 25864. And probably... Okay, does it work? Yeah, it worked. It's probably not gonna be... It has to be not done like that. So, yeah. But in any case, the goal for today was to actually learn how to handle the signals, the Posix signals in port. And I think we achieved that. So yeah, regardless of what is going on in here in the snake game, I think this stuff went well. So this is a Control-C, and I might as well actually put that in the examples, right, as a demo. To demonstrate how you handle the Control-C or stuff like that. So we can go into the examples, all right, and in here, so this is Control-C. I'm going to just move this thing in here. There we go. So that's pretty cool. It's kind of cool that it, like, this thing just works in port. But yeah. All right, so does anyone have any questions about what we just accomplished today, what we just implemented? So it's pretty cool. So let me do the following thing, by the way. I'm going to take the assembly program that we wrote, right, sig action, and I'm going to upload that to Gist for anyone to play with, right? So if you want to play with this thing, you can probably do that. So let me go ahead and just do that. Just So this one is going to be sig action.asm, and there we go. I'm gonna, oh my god, it is very, very inconvenient. Create secret gist. Thank you so much. All right, so you can find this thing in here. I figured out why it's straight up sec faults if you don't set up SA restorer. Do you want to check it out on stream? Is it something complicated? Because I was about to like sign off. Description. All right, so sig action assembly example. Oh, okay. So you just put it in the Discord. Let me check it out. I don't know where though, which channel. There's so many messages. Okay. After some digging, I figured out why it's straight up sig false if you don't set the SA restore flag. Okay, so something with Elixir. That's very interesting. Basically, it never sets up the rest of the stack frame. So when kernel exits the process, just starts running garbage sec faults. Oh, it's not Elixir, but it says Elixir. Okay, let me take a look. So that's the code. Can I just make it a bit bigger? Set up the return from user space. It provides the use step already. So if you set up restorer, right? Okay, and return code. And you just return. Oh, okay. So I suppose, yeah, it just like it never set up and exit the process, just starts running garbage and seg faults. I see. That's pretty interesting. So I'm gonna put that thing in the description as well. All right, it's pretty cool. All right, so that's it for today. Thanks everyone who's watching right now. I really appreciate it. We have a couple of subs that I actually missed. Katie-san, thank you so much for 2 months of tier 1 subscription. Akileos77, thank you so much for 4 months of tier 1 subscription. And Roman Codes, thank you so much for 10 months of Twitch Prime subscription. Thank you, thank you, thank you. So that's it for today. Thanks for all of these subscriptions, for all of the support. And I see you on the next recreational programming session. Thanks everyone. Love you.